So Dieter mentioned that we met in Max Planck Institute, and at the time, like right now, one would say on my side, right? So I don't know whether I have to accelerate or, so what time should we finish? Because it looks like we have already finished the session.
Half an hour is fine.
Okay. So I'm going to describe what we were doing recently at Manchester International Graphene Institute. We now managed to see quantum mechanics, not a big surprise, working, and actually working in solid-state devices at the room temperature, which is a certain surprise. In the talk that Dieter gave before the break, you saw temperature range of tens of millikelvins, but apparently to see the manifestations, the traces of Hofstadter butterfly, one better works at elevated temperatures, but in a different system. And that's what I'm going to show you at the end of the presentation. In the morning, Hofstadter mentioned that the best thing to do science is actually on a beach, where you can get nice ideas. And actually, this picture is from the beach which was branded the most beautiful beach in Europe for many times, at least 5. It is in Italy, in Gargano Peninsula, and that's where you can find a hint of what we're actually doing. Even color panel here is correct. By black, usually one means carbon, and this will be graphene in the presentation, and white is a name for boronitride, which is also called white graphite. And that's actually what we're doing at Manchester. We take graphene, we encapsulate graphene in between hexagonal boronitride sheets. Hexagonal boronitride is a very good material for encapsulation because it is atomically flat, it is layered as graphene is layered, and also it has a large band gap, so one can apply large voltages across a very thin layer of boronitride. Carrier density can be changed in graphene by a lot, and also one can perform very precise capacitance measurements, detecting small changes in the density of states of electrons in the system you want to study. And if you start seeing large variations, this would be indications for gap formation. Graphene is a system where the electrons are characterized by the Dirac equation close to the neutrality point of graphene. And what has been mentioned in the previous talk is that the Moiré pattern is also a characteristic feature of heterostructures between graphene and boronitride. And the parameters which matter here are the angle of the alignment between the graphene lattice and the lattice of boronitride, and also the lattice mismatch, which is unavoidable here because the two lattice constants are slightly different. And this small lattice mismatch determines the longest period that the Moiré pattern can have in graphene heterostructures with boronitride, which is about 14 nanometers. And this is a very comfortable range of distances to work with reasonable magnetic fields, not too high magnetic fields, to achieve conditions for even one flux quantum penetrating through the unit cell of the Moiré pattern theory. Also, what I would like to say here is that now one can control the alignment between the flakes to a very high accuracy. High accuracy means within half of a degree, and this is precisely the range where we're reaching this long wavelengths Moiré pattern. Also, to mention in the work that in the experimental work that simply exemplifies the structures that I'm talking about, it is paid, the attention is paid to aligning graphene with one of the, actually with the underlay of boronitride And then the other layer of boron nitride, which is used for the protection on the top, is not aligned with graphene lattice. So that all the Moiré pattern that I'm talking about is coming from one single interface, not being obstructed by possible commensuration between graphene lattice and boron nitride lattice on the top. To describe electrons in graphene, we use the fact that the Moiré period is long, so that we describe electrons in graphene not starting with the lattice model. We describe them in terms of the Dirac electrons in this two-dimensional material. And we have to keep in mind that for these Dirac electrons now moving in the presence of a periodic potential, one can use all what is written in textbooks about waves in periodic media, in particular that the group of translations is abelian, and its irreducible presentations are one-dimensional, and this makes it very easy to describe the states in the system for Dirac electrons taken in one of the Brillouin corners and one of the graphene valleys K, and similarly in minus K valley. One can do the zone folding using the Bragg vectors of the Moiré superlattice, and then within the new small mini Brillouin zone, one can use some model to diagonalize in the plane wave basis the Hamiltonian that would give you the dispersion of electrons in the newly formed minibands. These minibands are quite easy to describe, actually, both analytically and numerically. In the continuous model, where you would permit the perturbations coming from all types of the lattice effects, one can take into account that there is Dirac electron moving in a periodically modulated electrostatic background, and this is reflected by that this term in the Hamiltonian that we are using, it doesn't carry any Pauli matrices. The Pauli matrix in this Hamiltonian actually acts on the space of the electron components on the two sublattices of graphene honeycomb lattice, and other terms in this Hamiltonian, they characterize that locally there would be a difference on the A and B sublattice of graphene, and also the underlying substrate modifies the hopping between the neighboring sites, and therefore coupling between the two sublattices, and that transforms in a term which looks like a vector potential acting on graphene electrons, but it's not really a vector potential, it's all coming from the lattice effect. And in the analysis, one can pay attention to the symmetries, to rotational symmetry, to inversion symmetry. Inversion symmetry is, of course, violated here by the underlay, which doesn't have inversion symmetry. And the way how we do our analysis is we distinguish the terms in the Hamiltonian, which have different behavior in terms of inversion symmetry. In this model that we use, in the long wavelength description of electrons in this Dirac model in the presence of Moiré potential, we have phenological parameters which we initially didn't know at all. So what we did to do this analysis, we just went across a broad range of parameter space to identify what kind of minibands for electrons you're going to get. And then we did two things. We matched that to where in this parameter space a simple microscopic models would point the relevant part of the parameter space. And also looking at the outcomes, we would compare it with the experimental observations, both qualitatively and quantitatively, starting with the experiments performed at 0 and small magnetic fields. And what we found is that for the parameter range, which can be attributed to the microscopic models of any kind, we always end up with the miniband structure, which is shown in the bottom part of the slide. First of all, in this miniband structure, there is always no electron hole symmetry. The conduction band minibands and the valence band minibands in graphene look very different. We also find that there is a very well identifiable first miniband in the spectrum on the valence band side, which is terminated by something which looks like a Dirac point similar to the Dirac point in graphene itself. Even funny that the Dirac velocity in the secondary Dirac point is about 1/2 of graphene's Dirac velocity. Also, what you see here is that the Dirac spectrum of electrons in graphene is not very much affected close to the actual Dirac point, and the energy scale at which you start seeing the miniband effects is determined by the period of the Moiré superlattice, which is encoded here in the form of the Bragg vector of this superlattice multiplied by the Dirac velocity of electrons in graphene. And this energy scale can be between 200 to several hundred millivolts, depending on the period of superlattice, which depends on the misalignment angle between graphene and boron nitride lattices. So how does that show up in the experiments? It's still at a zero magnetic field. I mentioned that having seen boron nitride layers is good because one can measure capacitance very precisely, and that would reflect the compressibility of electronic liquid in graphene itself, and that can be converted into the measurement of the density of states of electrons. So that's what's done in this right-hand side panel, where this density of states is extracted from capacitance measurements. And what you see here is that the same dip in the density of states that corresponds to the linear spectrum in 2 dimensions appears at the high Fermi energy, to which we now can dope electrons by applying the voltage between graphene and the gate sitting on the top. And what you see here is that even the density of state values and dependence on the deviations from the minimum, they correspond pretty well to 1/2 factor that is produced by slower Dirac velocity of secondary Dirac electrons. Also, what you can see here is a spike in the density of states, which also tells us where on the energy scale the Van Hove singularity in the spectrum of minibands appears. In terms of transport measurements, it also manifests itself as similarity between the behavior of both diagonal conductivity or diagonal resistivity and hole resistivity as a function of the Kara density. When you cross from conduction band to valence band electrons, you have the Dirac point manifesting itself as a maximum in the resistivity, in the diagonal resistivity, in dissipative resistivity, and also as the change of sign in the Hall coefficient. And the same thing happens at the edge of the first miniband when you fill in the Hall states down to the first miniband edge, and you cross into the lower miniband in the spectrum of electrons in the presence of Moiré potential. One can also trace what happens with electron dynamics in a magnetic field, looking at, for example, electron focusing. Electron trajectories get curved by a magnetic field. You can detect it by seeing where electrons start in an injecting point and where they're detected when you inject current into graphene flake and use another contact for detection. This way to describe the structure of the Fermi surface in metals has been used for many years, and it's called transverse magnetic focusing of electrons. And what we did, we simply calculated for the minibands that we determined with the parameters we're now quite confident about, and compare with the measurements of the focus current taken at various levels of doping, therefore testing different parts of the miniband spectrum. And the experiment has been done at Stanford in Goldhaber, Gordon's group. And you can see that all features that the experiment has been shown have been shown in the experiment. They are also reproduced in the modeling that we did for the heterostructure of graphene and boron nitride. Now, if we go to stronger magnetic fields, the cyclotron curving of electron trajectories goes into the formation of Landau-Levels spectrum. Landau-Levels spectrum in graphene attracted a lot of attention, and it features the particular state, which stays at almost the same energy, at 0 energy, here tracing from the Dirac point up to high magnetic fields. And this non-dispersive Landau level is a feature which is also prescribed by the topology of the electronic states in graphene. I'm not going to go in such details here, but I would like to say that please remember this image because it will be useful for the following, just to compare different parts of the spectra that I will have for the superlattice. For electrons moving in the superlattice, one now has to do a bit of analysis. And the first point I would like to make is that in terms of the description of the states of electrons on the superlattice, one has to go back into the group theory with point having in mind raised by Aronov-Bohm physics for electrons propagating through the crystal, where they would scatter from different periodic sites and then eventually come to another periodic site interfering. And in terms of the group structure of the symmetry of states in a crystal in a magnetic field, it leads to that the translations acting on the states of electrons, they no more commute like they did at 0 magnetic field. They pick up an additional phase factor upon the commutation, which is determined by the Aronov-Bohm effect. And what it does, it produces a non-abelian group, which typically has infinitely dimensional reducible representations. And this is basically reflected by the infinite degeneracy of Landau level in the two-dimensional electron gas. And then Brown and Zach, when they looked at this problem from the group theory point of view, they realized that there are particular values of magnetic field that provide a rational value of magnetic field flux through the period of the crystal or through the superlattice unit cell in our case. And in this case, this magnetic translations group has a subgroup, which is actually abelian. And you can construct this group by simply taking the supercell, which is extended q times by the size of this denominator factor q, and in all directions. And in this case, the Aronov-Bohm phases will be equal to 1, and you get back the subgroup of this abelian group, of non-abelian group, which in terms of translations become abelian. And that means that for this larger size of the supercell, you can use all the same description of electronic states in terms of the plane waves, in terms of the Wannier states, but in a smaller mini Brillouin zone corresponding to a larger period of the superlattice that we had to choose to provide the integer number of flux quanta piercing this larger supercell in the description. So what it does, it produces the behavior of electrons that is exactly the same as in a usual crystal without any magnetic field, but this crystal would have q squared times bigger supercell. It would have q squared times smaller Brillouin zone as a result of that. And just by taking a view that the q square is too big to make it rational, it's enough to multiply it by q, not by q square, to realize that each of these states in the Brillouin zone will be also q times degenerate. And this is a nice result that one may keep in mind for the future, thinking about the physics of electrons in such magnetic minibands. And this is exactly what collectively produces a fractal spectrum known as Hofstadter Butterfly, illustrated for the tie-binding model on square lattice by Hofstadter. So what we had to do here was that we needed to use the continuous model. The tie-binding model doesn't really help us here at all. and we had to use some bases. And what we did, we adjusted the basis we used to the symmetry, the hexagonal symmetry of the superlattice. So we used non-orthogonal coordinate system, and we used Landau level basis for this, and then we used the superlattice potential that I described in one of the previous slides to diagonalize numerically and to get the spectrum of the system. So I plotted it here in the same way as in Hofstadter Butterfly spectrum, that the ticks indicate the energy intervals where we get the states as a function of the value of magnetic field flux piercing the unit cell of the superlattice. And we can track some of the groups of the states to the Landau levels of Dirac electrons, which you can see coming up together in the small range of fluxes, therefore small magnetic fields. And also you can track the groups of the states coming into what looks like the zero energy Landau level of the second generation of Dirac electrons, which appear at the edge of the first miniband due to the Moiré superlattice. But also what we paid even more attention to were the electron dispersions in those minibands, in those small Brillouin zones that we get for each of the values of P over Q for which we are able to do enough calculations to get the miniband spectra. And those miniband dispersions are actually quite important because those represent the hierarchy of the spectrum in the system and give a chance to observe the traces of Hofstadter butterfly directly and even at pretty high temperature. So if we just look at the collection of those minibands drawn on the bottom part of the slide, you can see that some of them are wider, some of them are thinner. And I don't really want to be obsessed about the gaps between those bands. What I'm interested in are actually the properties of electrons that would propagate moving around the crystal in those bands. If I think about those properties, that what will matter for me will be the typical group velocity of electrons in those minibands. The group velocity is a characteristic that you can approximately get by taking the width of the band and the size of the mini Brillouin zone. Here one has to be very careful just looking at the picture and trying to guess how it's going to look like, because the wider bands also have the larger support in terms of the size of the mini Brillouin zone. So one has to calculate these quantities really by taking enough points in the calculated dispersions, deriving the group velocity, and then analyzing this quantity. So the way how we look at it is that we think in terms of high temperatures. We think in terms of electrons propagating not just in one of those minibands, but in one or the other across the temperature energy range, which is covered by Boltzmann constant multiplied by the temperature in the system. And then if we look at what conductivity is determined by the Einstein relation, where the typical group velocity of electrons that move in the minibands is now taking as an average of several minibands in the spectrum, having in mind that we deal with the high temperatures. The only argument that I have to put forward to use this way to describe conductivity is to say that the lengths at which electrons undergo any scattering at all will be more than the period of this extended period of the superlattice, the period of magnetic superlattice, which will be several times the period of the superlattice itself if we're talking about the rational fractions which have not too large value of n in the denominator. And this constraint is much weaker constraint as compared to the constraint required to be able to see the gaps in the spectrum, which is a constraint that the temperature in the system has to be smaller than the distance between the bands and the sizes of the gaps in between the bands. So what we then did, we theoretically calculated the values of the typical group velocity averaged over several bands in the spectrum, or the energy interval corresponding to the temperature range used in the measurement. And those are shown with the dots. And what you see is that for the principal sequence of fractions like 1 over n, the values of this group velocity, typical group velocity, are higher. Then in this hierarchy of the band properties, the next range is given by the fractions 2 over 2n plus 1. And then we basically get all the rest, where we can still calculate 3 over 3n plus 1 or 3n minus 1, and then the computational power we have fails to deliver more points. But what you can see here is that the oscillations can be seen in the value of the mean square of the group velocity of electrons in the bands, and this is what should be picked up by the measurements of conductivity, of the diagonal dissipative conductivity in the system at high temperatures, at the temperatures where one would have no chance to see anything about the gaps in the spectrum if they are there. So what you can see as experimental evidence of that the Hofstadter butterfly was actually there in some form in terms of the properties of electron bands rather than the gap structure of the spectrum. It is that the experimental dependence of the conductivity on the magnetic field shows, the oscillation shows pronounced maxima, and these pronounced maxima appear not only at the values of magnetic field which correspond to our n fractions of the magnetic field flux quantum per unit cell of the superlattice, but also the obvious little peaks appear at the values corresponding to the 2 over 2n plus 1 fraction. One more point I would like to make is related to how you can look at what happens close to those simple principal values like 1 over n fraction in terms of the magnetic flux through the plaquette of the superlattice. For example, like it is illustrated here for the magnetic flux equal to 1/2 of the flux quantum value. So in this case, we can look carefully at the dispersion of the electrons in the minibands, and you can notice that the two consecutive minibands, they're separated by a small gap, and the dispersion is quite sharp near this miniband edges, magnetic miniband edges. Knowing this dispersion, you can even try to fit it with something, and it fits very well with a slightly gapped Dirac spectrum. And I told you already that Dirac electrons have very specific spectrum of Landau levels. They have one non-dispersive Landau level, which stays almost independent of magnetic field, or just independent of magnetic field. This Landau level is also separated by the largest gap from the rest of the spectrum. And if we look around this fraction 1/2 and look at the results of numerical calculations with exact diagonalization carefully, we can see that the spectrum of surrounding states looks exactly what you would get if you just take the parameters of this dispersion from the fitting of this dispersion exactly at the half-flux quantum value, and then use the Dirac model to diagonalize the simple Hamiltonian. So this is shown on the left-hand side, where black points are the calculated spectra, and the result of what you get from this is shown by the red lines. And this gives an interesting prospect for the physics of electrons in magnetic minibands. If you look at them from the same point of view as we already use in the description of physics of electrons in Landau levels at small magnetic fields. What is shown here on the right-hand side is the capacitance spectrum of graphene flake. graphene flake in a heterostructure with hexagonal boron nitride. And what is shown in black are the regions where the electron system is incompressible, basically indicating that there are some filling factors for the Landau levels of electrons for which Landau levels are completely filled. So if you look at the darkest paths, this corresponds to filling factors plus minus 1, and then you have plus minus 6, plus minus 10, which corresponds to the quantum Hall effect integer quantum Hall effect conditions for monolayer graphene. And this is where the system has the largest gaps created by magnetic fields and producing the strongest incompressibility. You can also see that you can trace the Landau levels filling corresponding to the zeroth Landau level and therefore filling factor plus minus 2, but now for electrons close to the first mini-band edge created by the Moiré potential. Also, what you can see here is within this plus-minus filling factor 2 range, there are additional lines which correspond to incompressible states, and those are actually due to the ferromagnetic exchange interaction between electrons. Ferromagnetic both in terms of the real spin of electrons and also in terms of the Bailey degree of freedom. And those states, which correspond to filling factors plus minus 1 and also 0, they have a gap which is determined by entirely by the electron-electron interactions. And then if you look carefully at the magnetic fields corresponding to the range near where you have flux quantum per plaquette of the superlattice, then being enlarged, you can see here the details which in terms of formation of incompressible behavior, which is very similar to what happens at small magnetic fields with electrons in just Landau levels, zeroth Landau level in graphene. And I think that this has a deep relation to the structure of the magnetic miniband at this particular magnetic field fraction, and this is fraction 1. And we see that the effect of the superlattice is the strongest in the numerical calculation when we look at the resultant spectra. And what you then can say is that in this around this value of magnetic field, the magnetic minibands in slightly different magnetic field values can be described in terms of the Landau levels, which split off the edges of the magnetic minibands at exactly one magnetic field flux through the plaquette. And filling those states to the effective integer filling factor can lead to, through the exchange interaction between electrons, can lead to the formation of incompressible states in the same way as the ferromagnetic exchange between electrons at small magnetic field leads to the new level of incompressibility related to the interaction effect. And this is a very interesting possibility, which basically tells you that you can take just one physical system, and by playing with the size of magnetic field, you can get a multiplicity of different quantum Hall physics, including the interaction effects. And I'm not even afraid of saying that in the future, maybe even fractional quantum Hall effect states related to the electrons now, not in the graphene bands, but in magnetic minibands in the presence of the superlattice. To conclude, I have told you about what happens with Dirac electrons in Moiré superlattices in graphene heterostructures with boron nitride. At low magnetic fields, we have very strong evidence and very clear behavior, miniband behavior of electrons in the Moiré superlattice. At strong magnetic field, we also start seeing the magnetic minibands predicted by Zahn and Brack, by Brown and Zach. And what I would like to say that I think that we only scratched the surface of the very rich superlattice physics in these heterostructures, and most probably the most interesting part of this physics is related to the interaction between the electrons when they are in these minibands. I would like to thank my collaborators who contributed towards what I described. On the theory side, these are the theorists in my group, and those who visited me while I was at Lancaster and after I moved to Manchester. And on the experimental side, the work has been done in Gaim's group, and most of the experimental effort was on the shoulders of this guy, Roshan Krishna Kumar, who was a course officer on several experimental papers on this topic. Thank you very much for your attention.
Yeah, thank you very much. Questions? We're all hungry.
More technical, you mentioned that you just use an effective Dirac model and tight binding is not necessary. Is it because it's, so you don't have intervalley scattering because the samples are so clear?
Yeah, because the wavelengths are big as compared to the lattice constant of graphene. And also the certain simplification comes from that the distance between graphene and boron nitride is longer than the period of the graphene itself. And what it does, it makes the simpler harmonics, which are basically determined by the Moiré pattern period, and kills all the finer structure that comes from higher order incompressibility effects between the two lattices.
Okay.
Are there further questions?
Yeah, I'm just wondering, is this unique to graphene on hBN, or maybe there are other combinations of materials that people look at, like TMDCs or?
There are several substrates that would give you almost squared 3 commerciability with graphene, which changes all physics because now you start coupling states in the opposite values. And those are also quite difficult to deal with because these materials are not so wide gapped, and they would start producing doping of graphene transferring charge from some impurities that are unavoidable as those materials at this stage, and that would make pretty low quality material. However, there is one group in Israel that looks at graphene on one of those.
Thank you.
So, further questions? If not, we have an announcement, but let's first thank the speaker again.
Well, there is one last thing for today that Professor Douglas Hofstadter has asked me to show all of you, and somehow I wish more of you could have seen this of the audience who were here this morning. It is a picture from old times in Regensburg, and it is yet another striking example of self-similarity if you look at the picture, and especially if you look at Douglas Hofstadter today. Could you please come up to the stage and make a few comments about that very picture as closing remark for this wonderful session?
Yeah, well, I deliberately wore this sweater today. This was the sweater that I wore all the time in Regensburg back in 1974-75, and I thought I had this picture in my talk. I was expecting it to come up sometime in my talk, which I formulated a few months ago, and I guess I left it out, and so I really wanted to ask you to put this up. Anyway, this is a lovely picture. There's Gregory Wanier on the right, Gustav Obermeier, who so generously hosted me in his laboratory, Alexander Rau, who we wish could have been here today, who was such a remarkable contributor to all of these things, and then myself, age either 29 or 30, depending on which time of my stay it was taken at. So this was a difficult period of my life, but at the same time it was a very rich period of my life, and it's so interesting to be back in Regensburg after, as we say, 42 years. And believe me, I don't know if you can understand this, but it's so weird. It is so weird to hear your name thrown around over and over and over and over and over and over again when you feel like you made the tiniest contribution by picking up a shell on the beach. And you picked up the shell, and then 1 million people admired it, and it's very bizarre. It's psychologically weird. It's pleasant, but at the same time extremely embarrassing and confusing. But I do appreciate the fact that, let me say, I appreciate the fact that I was so lucky to be on that beach at that time, right here in Regensburg with my friend, and thanks to my friend Rumpelstilzchen. That's it. Thank you.
Ja, ich glaube, das waren perfekte. Oh, maybe I should talk in English here. I think these were perfect words to end this little but very beautiful conference. Thanks for all the contributions. And just a very little announcement, there is another public talk this afternoon by Theo Geisel at 5, as you all may know already. Thank you very much.